Welcome to This Explainer. I'm your host, and today we're decoding the mechanics of light for the Cambridge Physics syllabus. We're going to trace light's incredible journey from basic straight-line rays all the way to how it's manipulated by complex lenses. Once you understand how light behaves, not only does the way you view the world fundamentally change, but you're also going to secure those top exam marks. Before we dive in, subscribe to our YouTube channel, Ace the Exams, at @aceexams_IGCS to excel in your Cambridge examinations. Let's get started.
It all starts with a simple yet profound question. How do we actually see the world around us? It's not magic, it's physics. For you to see absolutely anything, light must physically enter your eyes. It either travels directly from a glowing source straight into your pupil, or it bounces off an object and reflects right into your eyes. That is the foundation of optics.
Here is our roadmap for today's explainer. 1. The properties of light. 2. Reflection in plane mirrors. 3. Refraction and bending light. 4. Total internal reflection. And 5. How lenses manipulate light. Starting off with Section 1, the properties of light. Let's cover the basics of seeing. Light travels as waves, radiating from its source, but we always represent its movement in perfectly straight lines called rays. Right off the bat, there's a crucial distinction between what actually makes light and what just borrows it. Luminous objects, think the sun or the glowing screen you're looking at right now, emit their own light. But most objects out there are non-luminous. You only see a chair, a printed exam paper, or the walls of your room because an external light source bounces off them. It's a simple fact, but examiners love testing this basic difference. Now, take a look at how light bounces off different surfaces. Most things, like a standard piece of paper, are actually microscopically rough. So when straight rays hit them, the light scatters everywhere in a chaotic mess. We call this diffuse reflection. But on a perfectly smooth surface, like a mirror, the rays bounce off together uniformly, creating regular reflection. That's exactly why you can see your face in a mirror, but absolutely not in your notebook paper. Moving right along to Section 2, reflection in plane mirrors. Bouncing light. When you look into a perfectly flat plane mirror, the image you see follows some very strict rules. Rules you definitely need to memorize. First, the image is exactly the same size as the object. Second, it appears just as far behind the mirror as the object is in front. Third, the image is virtual, meaning light rays don't actually pass behind the mirror to form it. And the overarching golden rule governing all of this, the angle of incidence always equals the angle of reflection. Let's look at this geometrically to prove it. See the object labeled O at the top? The distance from O to the mirror is completely equal to the distance from the mirror straight down to the virtual image I at the bottom. If you draw a dashed line connecting them, it hits the mirror at a perfect 90-degree right angle, every single time. So how do you find that exact image, position yourself, say, under exam conditions? It's a simple step-by-step process. Draw an incident ray from the object to the mirror. Then construct your normal line, and draw your reflected ray leaving at the exact same angle. Repeat this entire step with a second ray at a different angle. Because it's a virtual image, those reflected rays spread apart in front of the mirror. Just take your ruler and extend those lines backwards behind the mirror. The exact point where those two imaginary lines intersect, boom, there's your image. All right, on to Section 3. Refraction and bending light, changing speeds. Here's where things get really interesting. What happens when light doesn't bounce off, but actually passes through a transparent material like glass or water? It undergoes refraction. Put simply, the light bends. But the crucial point to understand here is why it bends. It happens because different transparent mediums cause the light to physically change speed. This bending isn't just random. Back in 1620, a scientist named Willibord Snell discovered a mathematical relationship. Snell's law states that when light refracts, the proportion of the sine of the incoming angle, the angle of incidence, to the sine of the refracted angle is always a constant number. We call this constant the refractive index of that specific material. To see this math in action, take a look at the number 1.5. In a vacuum, light travels at a staggering 300,000 kilometers per second. But when it enters glass, it hits the brakes and slows to 200,000. If you divide the vacuum speed by the glass speed, you get exactly 1.5. That is the refractive index of glass. It's a precise measure of just how much that material slows down and bends the light. Mastering formulas like this is exactly how you jump up a grade boundary. So, subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE, to excel in your Cambridge examinations. Let's keep going.
Section 4, Total Internal Reflection, the water mirror.
Imagine a lamp sitting at the bottom of a pool. A light ray travels up through the water and hits the surface. Most of the ray bends or refracts away from the normal as it speeds up, entering the air. Notice that a very weak reflection also bounces back down into the water. This is pretty standard behavior. Now, let's move the lamp to increase the angle that the light hits the surface. As we do this, the refracted ray in the air bends more and more, getting closer and closer to the water's surface. Eventually, we hit a highly specific angle where the refracted ray bends so much it doesn't even exit the water at all. It just skims perfectly along the surface boundary. We call this specific tipping point the critical angle. It's the exact angle of incidence where the refracted ray runs completely parallel to the boundary at exactly 90 degrees to the normal. And remember, the specific degree of this angle isn't universal. It depends entirely on the transparent material you're dealing with. And here is the grand finale of this phenomenon. If that light ray hits the surface at an angle even slightly greater than the critical angle, refraction completely stops. Absolutely no light escapes into the air. Instead, 100% of the light is reflected back down into the water. The inside surface of the water is literally acting as a flawless mirror. This, my friends, is total internal reflection.
Human engineering takes brilliant advantage of this exact principle. High-quality periscopes, the kind used for looking over obstacles or in submarines, don't actually use regular plane mirrors. They use solid glass prisms. By designing these prisms so that light hits the inside wall at an angle greater than the critical angle, they achieve total internal reflection, creating a perfectly clear, 100% efficient bounce.
Finally, Section 5, How lenses manipulate light, directing the rays. Lenses generally come in two main flavors, and they're defined by their principal focus. A convex lens is thicker in the middle. It bends incoming parallel rays inward, converging them all at a single, real focal point. On the flip side, a concave lens is thinner in the middle. It bends parallel rays outward, making them diverge. Its principal focus is the virtual point backwards from which those rays appear to be spreading out. Let's see a convex lens act as a magnifying glass. If you place an object very close to the lens bends the rays. But because the object is so close, those rays don't actually cross on the other side. Instead, your brilliant brain traces those diverging rays backwards through the glass, resulting in a virtual image that is upraised and massively magnified. In physics, we don't just guess, we map this perfectly. By drawing just two standard rays on graph paper to scale, you can solve some really complex optical problems. By mapping one ray parallel to the axis and a second ray going straight through the absolute center of the lens, we can measure exactly where they intersect. This tells us the exact size, type, and distance of the resulting image. It's pure, elegant geometry and a guaranteed marker on your exam paper. From bouncing reflections to the calculated precision of lenses, I want to leave you with this final thought. Think about the device you are looking at right now. The screen is emitting light waves. Maybe you're wearing glasses, bending that light. Your eye itself has a lens doing the exact geometric math we just saw, focusing those rays perfectly onto your retina. You are literally experiencing everything we just talked about right at this exact second. Thanks for joining me on this explainer. And remember, subscribe to our YouTube channel AC Exams at acexams_IGCSE to excel in your Cambridge examinations. See you next time.